everyone, this is the third video for learning in nature's chemistry this week. You should have by now attempted to complete up to the end of page 22 in the notes. So you should have watched video 1 and 2, and you should have also watched 2 videos about experiments in which they carry out the oxidation of alcohols using different oxidizing agents. I'm just going to start this lesson with a little bit of an overview of where we are in terms of the learning outcomes. So we've been looking at carboxylic acids and oxidation of alcohols in this in the videos this week. So by now we should be able to give the definition of oxidation and reduction in terms of carbon compounds. So remember, that's an increase in the O to H ratio and a decrease in the O to H ratio. That's the SQA line for those. We should be able to work out the O to H ratio for different compounds. And we've got some stuff about aldehydes and ketones. That's what we're going to cover in this video. But you should also know already by now 2 oxidizing agents which are suitable for oxidizing primary and secondary alcohols, and state the colour change which occurs for each oxidizing agent. The video did indicate a little bit about the products of oxidation of alcohols, and you should know from the video that tertiary alcohols cannot be oxidized by mild oxidizing agents such as acidified potassium dichromate. So in the video I'm not going to give the answer to all of page 22 because I do want you to watch the experiment videos to get the answers for most of it, but I will just go over question 3. So question 3 says, why is the type of reaction involving the dichromate a reduction? So remember, in the videos previously you should have looked at the reaction of 2 different types of oxidizing agents, acidified potassium dichromate and a copper oxide. Remember, oxidizing agents are electron acceptors and therefore they themselves are reduced, so it's just saying why is this reaction involving dichromate a reduction. You should have simply said, if we look at the equation here, electrons are gained. You don't need to worry about anything to do with the O to H ratio when we're talking about anything other than hydrocarbons, so it's simply just that electrons are gained. Okay, so that's just going back to the oil rig definition of oxidation and reduction. Okay, so we're going to move on now to page 23, and in this page we're going to look in more detail at the reactions that are actually happening when different alcohols are oxidized. So page 23 begins with a little recap of a discussion of the definitions of oxidation and reduction in terms of hydrocarbons. So oxidation, remember, involves loss of electrons, loss of hydrogen or gaining of oxygen, and this results in an increase in the oxygen to hydrogen ratio. Reduction involves gaining electrons, gaining of hydrogen, or the loss of oxygen, and this results in a decrease in the oxygen to hydrogen ratio. I would really recommend spending a little bit of time trying to come up with your own way to remember these 2 definitions. So first we're going to look at primary alcohols. Primary alcohols are oxidized in 2 stages. First, they react to form substances known as aldehydes, and then they are further oxidized to carboxylic acids, which we do know about. So we're going to look at how this reaction happens, or at least the basics of how this reaction happens. So if you remember on the previous page, we mentioned that when we're reacting alcohols with these oxidizing agents, we can think of the oxidizing agent as a source of oxygen. So these aren't strictly your normal type of balanced equation because we don't really have a particular reactant in here. We're just saying plus O in this reaction, and we're just going to say that this oxygen is from the oxidizing agent, but we're not really going to give any details of the mechanism, the exact way in which the oxidizing agent provides the oxygen. Okay, so initially we'll just look at the structures in the notes. So when we have a primary alcohol and it's reacting with the oxygen provided by an oxidizing agent, we've got the hydroxyl group at the top here. And what happens is the hydrogen of the hydroxyl group, along with another one of the hydrogen atoms that's attached to that carbon, because remember in a primary alcohol, the carbon that's attached to the hydroxyl group has two other carbons, it's only connected to has two other hydrogens and it's only connected to one other carbon atom. So two of these hydrogens are going to combine with this oxygen to create water. And what then happens is, if this hydrogen is removed, this carbon will then have a spare bond. And what happens is the carbon atom forms a double bond to the oxygen of the hydroxyl group. So instead of the hydroxyl group, the carbon that had the hydroxyl group is going to end up with a new functional group that we haven't learned about before. We call this, it's going to be a carbon with a double bond to an oxygen, and we call this the carbonyl group. So I'm just going to show you how that works with the molymods. So if we start with a primary alcohol like ethanol, what's going to happen is that the hydrogen of the hydroxyl group is going to be removed, along with another of the hydrogens of the on the carbon that the hydroxyl group was part of. This carbon atom is then going to form a double bond to this oxygen here. I'm going to have to change the bonds around slightly so that I can use the flexible bonds to form a double bond. So you can see this carbon then forms a double bond to the oxygen. So this is the molymod of your aldehyde here. And then we also can form water in this reaction here. Okay, so this is stage 1 in the oxidation of a primary alcohol. We form something known as an aldehyde, which contains the carbonyl group, which is a carbon with a double bond to an oxygen, and then we also form water. Okay, let's look at stage 2, just in the structures initially, and then we'll look at the molymods. So in stage 2, with a primary alcohol, the aldehyde that was formed in stage 1 is going to undergo further reaction with oxygen provided by this oxidizing agent. And what's going to happen, and the mechanism for this is more complex, so we won't look at the details, but the carbon that's got the double bond to the oxygen is going to then form another bond to this extra oxygen. So this oxygen is going to be inserted between the carbon and the hydrogen, and hopefully you recognise this group here now that would be formed. This is the carboxyl group, and there's a wee spelling mistake here, I'm sorry about that. But what we form from oxidation of an aldehyde, which is then the second stage of oxidation of a primary alcohol, is a carboxylic acid, and I'm just going to label this the carboxyl group. So what's happening essentially in summary, when we have oxidation of a primary alcohol, the hydroxyl group is oxidized first to a carbonyl group, and the carbonyl group of an aldehyde can then be further oxidized to a carboxyl group and forming a carboxylic acid. If we look at the molymod version of this, so we've got our aldehyde here, and if we react that with some further oxygen, all that's going to happen is that the oxygen is going to add in between the carbon and the hydrogen. So if I just pinch this bond with this hydrogen on here, then we end up with our carboxylic acid. Okay, so we're now going to look at the oxidation of secondary alcohols. So secondary alcohols are oxidized to substances known as ketones, and this is similar to the first stage of oxidation of the primary alcohols. So you've got your hydroxyl group here, and the hydrogen of the hydroxyl group and the hydrogen that's attached to the carbon that's also bonded to the hydroxyl group are going to be removed from this molecule through reaction with oxygen to form water, and then the carbon will then have a free bond, which can then form a double bond to this oxygen of the hydroxyl group to form this group here, and again this group here is the carbonyl group. So both aldehydes and ketones have this carbonyl group, which again is just a carbon with a double bond to an oxygen. The difference with this compared to a carboxyl group is that we don't have the OH. So in a carbonyl group, we could call this R1 and R2, and in a carbonyl, neither R1 and or R2 can be OH. So they can only be a carbon or a hydrogen. Okay, so just to show you with the mods what's happening with a secondary alcohol. So remember, in a secondary alcohol, the carbon that's bonded to the hydroxyl group is also bonded to two other carbons. I've just added in a long bond here just to make it easier for me, but it doesn't really matter. So when we get oxidation of our secondary alcohol, the hydrogen from the hydroxyl group as well as the hydrogen on the carbon bonded to the hydroxyl group are going to be removed, and they will combine with the oxygen from the oxidizing agent to produce water. And then our carbon then has a spare space to form a bond, and it forms a double bond to the oxygen of the hydroxyl group. So we go from a hydroxyl group to a carbonyl group, as you can see here. So the carbonyl group, your carbon with the double bond to the oxygen, and these the product of the oxidation of secondary alcohols are known as ketones. So this is an example of a ketone structure here. Okay, and then finally, as you saw in the video, tertiary alcohols cannot be oxidized using mild oxidizing agents. And this is because the carbon chain would need to be broken. So in our tertiary alcohol, the carbon that's bonded to the hydroxyl group is bonded to 3 other carbons. So it doesn't have this hydrogen, which in the first stage, or in the oxidation of primary and secondary alcohols, gets removed along with the hydroxyl hydrogen to form water. So a tertiary alcohol, to do anything with this, we would have to break the carbon-to-carbon bonds, which tends to be less favourable when it comes to hydrocarbon molecules. So a tertiary alcohol cannot be oxidized. Right, just as a quick quiz, we're going to move on to page 24 now. But just before we do, as a quick quiz, see if you can remember the names of the substances formed when primary alcohols and secondary alcohols are oxidized. So we'll just cover this up here. Okay, so when primary alcohols are oxidized, the first product would be what? Hopefully you're saying aldehyde, and the aldehyde is then oxidized to what? Hopefully you're saying carboxylic acid. And then when secondary alcohols are oxidized, the product is what? Hopefully you're saying ketone. Okay, so we're going to move on to the next section, and in the next section of the notes, what we're going to focus on is we're going to focus on these aldehyde and ketone structures and how we name these and draw their structures as well. Okay, so you should have moved on now to page 24. Aldehydes and ketones. So aldehydes and ketones are 2 examples of carbonyl compounds, as they contain the carbonyl group, which is given here. So you might be asked to circle the carbonyl group in a structure, and if you were asked to circle the carbonyl group, you would just circle the carbon and the oxygen. First we're going to look at aldehydes. So aldehydes contain the carbonyl group at the end position of a hydrocarbon chain. Their names end in al. So we've got aldehydes generally, which contain the carbonyl group at the end position of a hydrocarbon chain, but then we also have something called the alkynyl homologous series. So the alkynyl homologous series corresponds to the parent alkane. So basically we've got the aldehyde, the carbonyl group at the end of a chain, and then the rest of the chain, if it's an alkynyl, is just single carbon to carbon bonds with hydrogens. There's no double bonds or anything fancy. So the alkynyl series corresponds to the alkane series with the ending changed to al. The carbonyl carbon is numbered 1. So when we're naming, the carbonyl carbon is always numbered 1, but we don't, when I say it's not written, I mean we don't need to say hexan 1 al, for example, because if it's an aldehyde, if it ends in al, then the carbonyl group is always at the end of the chain. Okay, so al tells us that the carbonyl group is always at the end of the chain. Okay, so when it comes to naming alkanals, very simple. We just need to count the number of carbons for straight chain ones, and then the rules for branched chain are very similar to the previous examples of naming that we've looked at. So what I'd like you to do is draw the structural formula for the following. I'm going to go through the first one and then I would like you to pause the video and try the others. So first we're going to look at methanol, and methanol is the systematic name, but you might often, if you ever see this, you might see it's called formaldehyde. It used to be called formaldehyde, but that's still pretty commonly used. I think formaldehyde is used for preserving biological specimens, body parts and things. I could be wrong, but I'm pretty sure that that is the case. So meth tells us there is only one carbon in this molecule. Methan, and then it ends in al, tells us that it's an aldehyde, and that means that the carbonyl group is at the end of the chain. Well, there's no chain, obviously, because we just have one carbon atom. So we're just gonna have, oh, I'm doing that in a terribly messy way. We're just gonna have one carbon atom, and it's going to have a double bond to the oxygen to form the carbonyl group, and the other atoms in the molecule, because carbon has to form 4 bonds, are just going to be hydrogens in methanol. I'll just try and draw that a little bit more neatly here. Okay, so pause the video now and try and do 2, 3 and 4 of this question. Okay, so here are your answers here. Notice a couple of things about the way I've drawn these structures. First one is that I've drawn the double bond O and the H kind of at this angle rather than straight up and down, and that just reflects the angle that's actually present in the molecule. And then another thing is that you can draw them either way round. So as you know, with these structures we could pick them up, flip them over. So we could draw ethanol like that. We could draw it the other way round as well. So butanol I've drawn with the carbonyl group at the left hand side of the molecule. It really doesn't matter. So while we're here, I'm just going to go through the shortened structural formula for the alkanals as well, because there's something that you should recognise about the shortened structure, and in fact it's up here. When we write the shortened structure, we write the carbonyl group in an aldehyde as CHO. So you should recognise if you see CHO, that's telling us that it's an aldehyde. So just for example with these ones, this one's going to be, take this carbon for the shortened structure, it's CH3, this one, we could, again, it's carbon bonded to an oxygen and a hydrogen, but rather than writing COH to show that it's an aldehyde, we write CHO. Okay, so this one again, to be honest, I would probably, if I was writing the shortened structure of butanol, I would probably still take it from this end so that I get my CHO at the right hand side of the shortened structure. So I would write CH3. I'm going to go from right to left in the shortened structure this time. CH3, CH2, CH2, and then CHO. So this is one sense in which it's probably better to always write the shortened structure from the end that's furthest away from the carbonyl group, so that you end up with the CHO at the end. This one here, the shortened structure would be CH3, CH2, then CHO. Okay, so we're going to move on to question 2 now. If you haven't already done it, you've got to write the molecular formula for the above in the form CXHYOZ and use this to work out the general formula for the homologous series. So I would probably just do it for the 3 of them here, and then try and work out the general formula. So pause the video now and make sure you have a go at that. Okay, so hopefully you're agreeing with me. So I've got the molecular formulas that I've written out here, and then the general formula CnH2nO. Right, we're going to move on now to page 25. And in page 25, we're looking at the naming of branched alkanals. So I'm going to run through the first one, I think, and then I'll get you to complete the second 2. But if you want to, you can pause the video now and give them all a try. So we've got 2-methylpropanal, and we've got to draw the full structural formula. So remember, we don't need to specify the position of the carbonyl group, because if it ends in al, we know the carbonyl group's at the end of the chain. So what do these other parts of the name tell us? First of all, what does prop tell us? Hopefully you're saying that there are 3 carbons in the main chain, which you would be correct about. Okay, what does 2-methyl tell us? Well, hopefully you're saying that means that there's a branch with 1 carbon on the second carbon, carbon number 2. Okay, so I'm just going to draw the skeleton of the carbons, and then I'm going to add in the functional group and the rest of the hydrogens. So it's propanal, that's telling us it's got the carbonyl group. So it's got a double bond to an oxygen here, and then just a hydrogen here. Careful that you don't get the carbonyl group mixed up with the carboxyl group and accidentally draw an O and then an H here. That would be a carboxylic acid, not an alkanal or an aldehyde. Alkanal and aldehyde are kind of interchangeable at this level, but it's just that we could have something that's an aldehyde, but because it's a more complex structure, it wouldn't be an alkanal because it wouldn't follow the general formula that we just wrote on the previous page. Okay, just putting in the hydrogens now. Okay, and then the shortened structural formula, again, very similar to how we've done it in the past. So we take each carbon in turn in the main chain, and we write what's around it. So we've got carbon with 3 hydrogens, CH3, a carbon with 1 hydrogen and a branch. So remember the branch goes in brackets, so CH, CH3. And then we've got the carbonyl group, which we learned on the previous page, that we write CHO. Okay, so pause the video now and see if you can complete these other 2 structures. I'm not going to give you the answers to these just now though, I'll ask you to send in your work for this. Okay, so if you're watching this, you should have completed page 25. We've now moved on to page 26 of the notes, and we're going to look at ketone structures. So how are ketones formed again? Well, hopefully you're saying from the oxidation of a secondary alcohol. So ketones contain the carbonyl functional group in the middle of a hydrocarbon chain, whereas aldehydes contain the carbonyl group at the end of a chain. The names of the alkanone, and I think there's a wee spelling mistake here, this should say alkanone, so sorry about that. And that's quite a significant spelling mistake because the EN would imply that there was a double bond, whereas AN implies that there are only single carbon-to-carbon bonds, which is what I actually mean. So let's make sure you change that. The names of the alkanone homologous series of ketones correspond to the parent alkane, with the ending changed to -one. So again, ketones, we could have this carbonyl group, it could be a ketone, part of a much more complex structure. The alkanones are a homologous series of ketones which are similar in structure to the alkanes, but with a carbonyl group here. And they are named by counting the longest chain, including the functional group, numbered from the end nearest to the carbonyl chain. So a similar, to the carbonyl carbon. So similar rules to what we've learned about in the past. So just things to emphasize here would be the -one ending to tell us that it is a ketone. And then, unlike with the aldehydes where we didn't need to give the position of the carbonyl group because it was always at the end, with the ketones we need to specify the position of the functional group, and like with their other substances that we've named, the position of the functional group goes between the "an" and the ending of the name. It's easiest probably to get with some practice. So you've got an example here. We'll just look at this one actually. So this is hexane 2-one. You'll see that the shortened structural formula for ketones is written, the carbonyl group is just written as CO. So if you see COC in a shortened structural formula, that should tell you that this is a ketone. Okay. Question 3 then tells you to draw full and shortened structural formula for the following. So again, I'm just going to maybe do the first one with you, and then I'll get you to do the rest. So first one is propanone. So propanone, how many carbons is it going to have? Hopefully you're saying 3. Okay, so we've got our 3 carbons. And with these, with the first 2 examples, I would, well, there's something kind of slightly special about them actually. We'll maybe talk about both of them. So for it to be a ketone, if there's only 3 carbons, the only possible position for this to be a ketone would be for the carbonyl group to be on the middle carbon. If the carbonyl group was at either end, this would not be propanone, this would be propanal. Okay, so that's why we don't have to say propan-1-one. Propan-1-one wouldn't be correct because there is only one propanone, okay? There's only one propanone. So we're just going to fill in the rest of the hydrogens. This carbon in the middle, 1, 2, 3, 4, already has 4 bonds, so it's not going to be bonded to any hydrogens, and the other carbon would have 3 hydrogens as well. So we said full and shortened structural formula. So shortened structural formula, taking each carbon in turn, CH3, CO, and then CH3. So you're seeing, if you're seeing COC, then you're thinking ketone. Okay, so similarly butanone, but means how many carbons? Hopefully you're saying 4. 1, 2, 3, 4. And again, if I put the carbonyl group on either this carbon or this carbon, it would be butanal. But no matter whether I put the carbonyl group on this one or this one, the way I would name this molecule would still be butanone. And it would always be, the carbonyl group would always be on carbon number 2, so we don't need to specify, we don't need to say, so I'm going to just emphasize that, not butan 2-one, because there is only one butanone. If it wasn't butanone, it would be butanal. There aren't any other possible options other than butan 2-one, so we don't need to give the position of the carbonyl group in this case. So we can draw it at either side, and then again we're just going to add in the hydrogens. Okay, so I'm gonna just make that a little bit neater. This is a little bit awkward because I'm watching this on my screen rather than watching the pen. So just try and make sure your bonds go nice and neatly from the atom that they're actually, between the two atoms that they're actually joined to, rather than going off into space too much, which is what mine were doing there. Okay, so pause the video now and try and complete the rest of question 3 and question 4, please. I hope you've spotted my mistake here. So get rid of that hydrogen because that carbon already had 4 bonds. Okay, and I've also had to add in a hydrogen. So I've just fixed my structure for butanone. I hope yours was okay. You might have done a better job of that than me. And this should be the correct shortened structural formula for butanone. So if you haven't already, pause the video now and do the rest of question 3 and 4. Okay, so you can see the answers to the rest of these questions here. So this is pentan 3-one and then octan 4-one. Notice that with octan 4-one, you could have drawn it the other way up, so with the carbonyl group on this carbon instead, and you could write the shortened structural formula in 2 different ways, so I've drawn them both here. So here are your molecular formulas and your general formula, and what do you notice about this general formula? Okay, hopefully you might be saying it's the same as for the aldehydes. So aldehydes and ketones are isomers. So the ketones, or rather alkanones, because we're specifically talking about the alkanone homologous series, and they are isomers of the alkanals. So you can impress your families with that fun fact there. So the alkanones are isomers of the alkanals. Okay, we're just going to move on then. Last page that I would like you to do in this session is page 27, and that's just looking at branched ketones. So we're going to look at I've got one more question. So why is it not possible to produce methanol or ethanol? I'm going to leave you to ponder that because I'll ask you to hand in this this page here. And again, we're going to look at branched ketones, and I'll just look at the first one with you, and then I'll get you to do the other 2. So we're going to look at 4-methylhexane 2-one first. Okay, Again, if you're confident with this, pause the video now, it's absolutely fine. So again, when we're having to draw it based on the name, I prefer to look at the ending first. So hex means what? Okay, hopefully you're saying 6 carbons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's hex and 2-one. So the carbonyl group is going to be on carbon number 2. Doesn't matter whether you draw it on this one or on this one, as long as you get your methyl group in the correct position comparatively. For the change, I'll go over this side this time with my carbonyl. So carbon 1, carbon 2 with the carbonyl group. And then it's 4 methyl, so 1, 2, 3, 4. What does the methyl mean? 4 methyl. Hopefully you're saying branch on number 4. So that's us. Now, we've got to be careful with our carbonyls not to put, as I did in the previous page, a hydrogen on the carbonyl carbon because it already has 4 bonds. So we're just going to fill in, but we do need 3 hydrogens on this carbon here. So just trying to get that right. Okay, fab. And then your shortened structural formula, CH3, CO, CH2, C, and this carbon has a branch, so we're going to put the branch in brackets, but it's also got a hydrogen, so it's CH, CH3, CH2, and then CH3 at the end. Okay, thank you for listening to this. Make sure you try the rest of question page 27, and then we might have some other questions for you to have a go at as well, but I'll make that clear in the assignment. Okay, so first of all, apologies, I know I said the last page was the last page, but actually it's going to make much more sense for you guys if you just do page 28 this week as well, as it fits in with everything else that we've been doing. So page 28 is oxidation of alcohols to make aldehydes and ketones, and it's some practice questions. So this is putting everything together now. We looked at what is formed when different types of alcohols are oxidized, and then we also looked at aldehyde and ketone structures, and this is just making sure you're comfortable linking up the two. So there are 4 questions on this page. I'll go through question 1 with you, and then I'd like you to complete the rest and submit these on Teams. So this is just a little reminder from page 23. So if we've got a primary alcohol, that will be oxidized first to the corresponding aldehyde and then to a carboxylic acid. So we've got 2 stages of oxidation there. If we've got a secondary alcohol, that will be oxidized to the corresponding ketone, and if we have a tertiary alcohol, it cannot be oxidized. So question 1 says write an equation using full structural formulas for the oxidation of butan-2-ol in part A, and then we've got to write a word equation afterwards. So definitely the first thing to do with these questions is to first of all figure out whether you've got a primary, secondary or a tertiary alcohol. So you can look back through the notes if you're not sure about that. I can't remember what page it was, but I'm sure you'll find it. And then also to figure that out, you probably want to be drawing out the structures. So we're going to draw butan-2-ol. So first we look at the prefix to tell us the number of carbons. So how many does but mean? Hopefully you're saying 4. So we're going to have 4 carbons in butan-2-ol. And we are going to have the hydroxyl group on carbon number 2. So I could draw it either way, because remember, I would number the chain from the end closest to the hydroxyl group anyway, so I could draw my hydroxyl group here, and it would be on number 1, number 2, or I could draw it here, and then this would be number 1, and this would be number 2. So it doesn't really matter, I'll just draw it here. And then fill in all my hydrogens. Okay, super. Now, we don't have to, it hasn't told us the oxidizing agent that we're using, so we don't have to include any oxidizing agents. And to be honest, I wouldn't even bother including, if you want to, you can put the little O and put loss of water, but you don't have to. But maybe it is best to put that in, okay, because just to show that this is oxidation. So we've got our butan-2-ol, and we're doing oxidation. So this, first of all, let's look at to figure out what type of alcohol it is, we look at the carbon that's attached to the hydroxyl group, and then we look at how many carbons it's attached to. So this carbon here is attached to 2 other carbons, and this means that butanol is a secondary alcohol. And if it's a secondary alcohol, it's going to be oxidized to the corresponding ketone. So what I would do would just be to draw out my 4 carbons again, because remember the carbon chain doesn't break when we're doing these oxidation reactions. What happens is that the hydroxyl group changes into a carbonyl group, so that's why a secondary alcohol will go to a ketone. So we're just going to change the hydroxyl group for a carbonyl group like this. And if you're struggling, page 23 has examples for all the different structures again. So now we're just going to add in our hydrogens. So remember, in a ketone, this carbon here already has 4 bonds. You saw me making that mistake earlier and adding a hydrogen in here, but we don't need to. This carbon though will have 3 hydrogens. This one will have 2, and this one will have 3. And we've put our little O in here because this hydrogen and this hydrogen are going to be lost to create water in combination with the oxygen that's supplied by the oxidizing agent. Okay, and then writing a word equation for the reaction. Well, the name of this one was given in the question, so obviously this is butan2-ol. And for this one, I would just write oxidation under the arrow, because like I say, we haven't been given the name of any particular oxidizing agent, so I wouldn't worry too much about that. And it's going to create, well, this is a ketone with 4 carbons, and if we remember, because if it's a ketone, the only position for the carbonyl group to be in is number 2, so we don't need to say butan2-one, we just need to say butanone, because there is only one option for butanone. Okay, so to be honest, when you're doing these types of equations, you don't necessarily need to put in the oxygen and the water. Really what we're just looking for is for the alcohol changing into the aldehyde or ketone or carboxylic acid, whatever the product is, but you can if you want to. Okay, so we've got question 2 here, which is similar to question 1, but again you're going to have to figure out what type of alcohol and what the products will be. It does say both stages, so that gives you a little hint. And then question 3 and question 4 down here. So make sure you answer those. Thank you for listening to this video, and I hope you get on okay. Make sure you let me know if you've got any questions. Bye.